Hello. I told I will make a video after 10th. I did make a video after 10th. Okay, so I took 2 days gap. Yeah, I know. Actually, there was an exam and I took a little bit of rest after that. Yeah, 2 days rest. Okay, anyways. So we said that we'll be working on CIFAR 100 and yeah, I have already completed CIFAR 100, but I didn't show you the code. So today I will show you the code and most importantly is uh, I've written all the code when I posted those CIFAR 100 videos, but I didn't get time for recording. So today I'll just explain the whole code, and today I will show my next video plans. So next, I will just show a glimpse of the next video. So this is the data set. This is the data set that I'll be working on my next video. This is Brad's data set. This is actually brain tumor segmentation. So we'll be doing all these, and my next video, from next video, it will be a total uh, videos, a series of videos for my total projects. So yeah, I might take some time uploading because main reason being I don't want to uh, publish the video. I mean, I don't want to upload the videos before my project is finished. So there might be some privacy issues. So I will do it slowly. But yeah, those that will be available. I mean, those that can be uploaded. I will upload it very fast. So there will be series of video from this month only. So let's start with the CIFAR 100. I think I shouldn't take much time because it's only about explaining the code. So let's start about with CIFAR 100. I will put the code on GitHub and I will share the link. Okay, so I think it should be here. So it's not. Sorry, I'm sorry. I'm sorry. Projects. Yeah, I think. Yeah. Okay. So this is the code. Uh, and I will put this on GitHub as I said. So let me show you code one by one. Previously, I've said that in how to unpickle a file, how to extract the data and all. So here, what we will do, we have integrated that unpickle function and all. So that's a different file actually. I will not show that. Okay, let me show it once. Uh, this is the this is the previous file that we are working on, but we have integrated it, so it's not needed. This one is not needed. So anyways, so please refer to the video because sometime I will say that as a reference. So please refer to the video and if you want to fully understand this one. So let me first tell you about what is a machine learning model. So machine is actually like a baby. So uh, you have to teach the machine what is what. So first I'll show the machine an image. So this is a pen, right? This is a blue pen. So I'll say that this is a pen. I will show the image and say that this is a pen. So then the machine or the baby will learn, okay, this is a pen. That's nice. Next time, this is a training. This goes into the training. But next time I will show as a testing. So that was a blue pen, right? So next time I'll show this and ask, what is this? If the machine is able to say that yeah it is a pen, then it's a good model. So the machine has extracted the features only required to be, only required so that it becomes it so that it indicates that this is a pen. But if it extracts features like the color and all and puts it into the primary features, then it's not a good model. Because like if the machine says that this is a pen and this is not because the colors are different, so it's not a good model. So we have to train the machine such that machine only captures those features which are required for identifying a picture, not the unnecessary features. If we put too much features, then the machine will not be able to distinguish and uh, classify images. Like this machine will treat these as two different objects, so that's not required. So for that as I told you, there will be an image, and there will be there will be something that will say that this is what. So this is a pen. Like, for that will have an image and a label to refer to that image, saying that what the image is actually. So um, that's the that's how the machine learning code works. So here we have unpickled the file. We have the trained dataset, the test dataset, and the metadata. Metadata contains the data about these datas. So metadata contains how um, what are the file names, what are the uh, categories and all. So these are all the metadata files. So we've printed that how many training datas are there. There are 50,000 training data. I mean, that means there are 50,000 images. And then then we have defined an array. We have defined an array which contains the list of categories in which the images will be categorized. So this is the image will be categorized into all these 100 categories. We have the list of 100 categories: apple, aquarium, fish, baby, beer, and all these. Like, we have put it into an array. We will need this in the end of the code. So I did it here. Anyways, so now we have xtrain. Xtrain contains all the uh, images that will be required for training. Okay, so there will be two parts: training and testing. Training is where the model trains and learns which image is what, and testing is contains a separate data set of images which will ask the model and tell the model to predict which image is what. uh, and then we will compare the actual data of the test dataset and the predicted data and compare the accuracy. So here is the training data. So in the training data we have linear arrays, which are actually images. Actually, image is what? Image is a matrix of values. So here we have 1D matrix, so we have to convert that into a 2D matrix. I have done it in the previous video, so please refer to the previous video for this part. And next, uh, we have reshaped it all. And okay, y train contains the labels, as I told you just now. Y train, okay, we have images and labels. X train and X test contains the training data set of images and testing data set of images. Y train and Y test contains the uh, training dataset of labels, and labels of the training dataset and labels of the testing dataset respectively. Okay, so then we have to specify the number of classes in which it will be classified. So these are 100 classes. And next, okay, so what is this? We have written that xtrain is equal to xtrain by 255. Why we have done this? Because 255 is the highest value of the matrix, because it's an RGB image. So we have normalized the image and put the value from 0 to 1. Okay, so why I have done this? Because this helps the computer to compute fast, and the values will not go very high, for because these are a series of mathematical calculations. The values will not go very high when we uh, put the values in the matrix from 0 to 1. So it will be faster, and uh, helps the computer to compute faster. So anyways, next we have initialized the model. So this is the model in which all the images will be fed, and and finally the output will come as the output will come, and then we have to predict the model, predict those test images, like that. So uh, first we have to name the model. So model, we have named a model, and then we have added a so if you have to know about convolution layer, I will add a link in the bio, in the description. So he's a teacher in YouTuber, and he uh, have I mean he did an he made an amazing video on convolution layers in a very easy method. So I will put that link, and please refer to that link, and uh, you will understand about CNNs and what are convolution layers and what are max pool layers and why dropout is used in all these. So please refer to the video so that you can understand these codes and all easily. So we have convolution layer. uh, the filter size will be 64. Again, we have another convolution layer, we have a max pool layer, we have a dropout of 0.2. Then again there will be a convolution layer, max pool layer and all. Then again, and then finally we have flattened the matrix. And then we have the dense layers. Those are the interconnected hidden layers. We also call that as hidden layers. So we have dense layers. There are, I think, one, two, three dense layers. And finally the output layer. So we have used an activation function in each layer. These are the ReLUs, and I think in the last we have used an activation of softmax. Yeah. So these are model summary actually. So these are the all total number of parameters, and all of them are trainable parameters. Next, we'll mention the number of epochs. Epochs are actually number of cycles in which the training will go, number of times the training will happen, and the batch size. So how many number of images will be taken at one time while training. So these are the epochs and batch size. We have used Atom Optimizer, and learning rate is 0. Learning rate, we keep learning rate very low because it helps to I mean the accuracy is reached very the accuracy is precise. I mean the what should I say, the model accuracy is better for low learning rates. What are the disadvantages of low learning rates? Takes more time. In simple word, it takes more time. So these are the advantages and disadvantages of low learning rate. But our main motive is to have a higher accuracy. So we, at present, at present circumstances, we have a lot of time, so we keep the learning rate very low and to gain higher accuracy. So then we compile the model with loss categorical with loss function as categorical cross entropy. And then what we do is we mention an early stop. So for avoiding overfitting of model, we apply early stop, so that when the early stop is actually like when we know that the model overfits. Okay, so there is a function, we can know by the loss function that the model is overfitting or not. If the model starts overfitting, the loss function will go up. So as soon as the loss function goes up uh, continuous, sometimes the loss function does go up. I'm not saying that loss function doesn't go up at all, but sometimes it happens that it is, I mean, while training, like loss function, it will initially will be at higher rate, then it will initially come down, sometimes it might go up, again it will come down. But if this happens that the loss function is going up and up and up, it is increasing continuously, the model should be immediately stopped so that overfitting doesn't happen. So so these are the this is the function where the model should be stopped in case there is a overfitting in the model. And then there is a model checkpoint. So model, when we have a CNN model, we have something known as weights. Okay, so uh, which what should I say, parameter, which feature should have a higher weight, I mean higher value, I mean what should I say, value, higher priority, which feature should have a lower priority. These are all the weights. Okay, so we have to save in CNN, the weights automatically change, and we find a uh, we find a what should I say, optimized model, where optimized weights in which the model have the highest accuracy. So we save these weights for future use. So for future image prediction, we save these weights. So here we have this is the model checkpoint, so where the weights will be saved at uh, by which name the weights should will be saved, and what will be monitored. Actually, validation loss is monitored for most of the time. So if the validation loss and the mode is minimum, so with minimum validation loss, the weights will be saved. So like validation loss is maximum and initial, then it decreases. When the validation loss is like, for every decrease the weights will be saved. Like for initially it's something like, say a random number 10, maybe 10. So validation loss is 10, and then in the next epoch the validation loss is 9. In the next it's 8, in the next is 7. So every time it decreases than the previous values, then the weights will be saved. Next, at some time the model will be at its best optimized weights. After that, if the model continues to train, the validation loss will start increasing as due to because of overfitness. So when the model starts getting overfit, the validation loss increases. Then only the model will have 10, 9, 7, 6, 5, 4, 3. For example, till 3 we have a validation loss of 3. Next, the model will start going up 4, 5, 6. So our minimum validation loss, weights at the minimum validation loss will be saved for future use. So we will have the weights for the best optimized model for this data set. So next we have the data gen. So data gen actually image data generator. It actually takes random images and then twist and turns. For example, let me show you. So this is a pen. What is this? This is also a pen. What is this? This is also a pen. So the image will be twisted and turned and flipped. These are all the functions that will be done so that the computer understands that if this is a pen, this is also a pen, this is also a pen. So we will show all the possible ways a pen can be image can be shown, and so that for any kind of images, whether it is twisted and turned and all, the result is always the same. So we have to change we have to we have to use this function as data gen in training dataset and validation dataset, and then we train the model. Okay, so this is the model history is equal to model fit. We fit the model in the dataset, and so these are the steps per epoch, and these are validation steps, and the callback. I just said what is callback. The callback is what we have last saved as the best weights for the best optimized weights. So this is the callback, and then so the training is done. The training is done. Well, I'll show you. See, at 76 the validation loss did not improve from this, and the validation loss kept going, maybe increasing than the last value. So we have we stopped, and as we stopped our I think the yeah at epoch 58 the last best validation loss we have captured. So we saved that model. Then I will show you the figure how the validation training accuracy and validation accuracy and training loss and validation loss took place. So the loss decreased with time. You can see the loss decreased. So you can see that sometimes the loss increased, but again at the next epoch it decreased. So it increased and decreased in this pattern, and training loss is all does always decrease with each epoch. But what we have to focus is on the validation, not on the training. So yeah, it decreased, and yeah, we can see that the training accuracy increased, but validation accuracy also increased. And yeah, these are all the things that we can see. But most importantly, what is the accuracy? Accuracy is validation accuracy is 56.78% and test accuracy is 57.57%. So the test accuracy is the test data set, and validation loss, we can see validation loss and the test loss is 1.73 and 1.75 respectively. And next we have to show that what is our model actually showing, right? So very important, random. So we will need that, we'll show you why. So I have imported this. Actually you don't have to, but generally I do, because maybe I have mentioned some variable earlier, so it might clash. So just for this part I just do I just override all those variables and do my thing, just like as I don't need those variables anymore. This is the last part of the code, so I keep doing all this. I again write all these codes. I just copy pasted from my this part. I copy pasted from this part only. There is no big issue in all these. So anyways, I copy pasted all these things, and then then I mentioned the file, the test dataset actually, and I used all these dataset keys. These are not important. Then yeah, Then I have selected an image index of 220, right? So this is a random image in the test dataset, and I have reshaped the image so that it can be shown. It's actually 1D matrix, so I've reshaped into a 2D matrix so that it can be shown in the computer. And then I predicted the what our model is predicting actually, and I also showed what is the actual value. So our model predicted that this is a wardrobe, and actually is also this is a wardrobe. So why did I use random here? I used random here to randomly show any image in our data set. So actually I can show this, yeah, it's a GPU. Okay. Actually I have to run uh, all these keys, all these codes again to run this. Actually I don't think fits. Let me see whether, yeah, I have to run all these oh damn it, dude. Wait, let me see whether, yeah, I have to run all the codes again. So I will put the codes in GitHub. If you want, do it on your own. I'm not running it again, it takes a lot of time. So anyways, this is all about CIFAR100. And uh, anything else you want to ask, you can ask in the comment section. So this is our accuracy, and I just showed that how the model is predicting. So anyways, thank you. And I don't know how much the video went, I will just check. Anyways, that's all about CIF100. We'll be working on brats from next week actually. So thank you, and see you in the next video. See ya.
Please subscribe.